Hello and welcome back for part 2D of Homework 2 for Computational Methods. Today we're actually going to look at Broyden's method itself and derive his method for an iterative refinement of the approximate Jacobian. So, if you remember from the previous video, Broyden's method is it's a derivative of Newton's method for finding roots with more than one variable. It's very useful when you're looking at, a lot of variables. So what specifically we're going to be looking at is we're going to be looking at this equation here. Let me zoom in, which is designed as a modification of the approximate Jacobian based off of this. It's kind of so it's he kind of used the secant method that we talked about in part 2A as kind of a baseline for doing this. And we're going to derive this kind of in term to show exactly how he got there and why it works and why it makes sense. So I have here a blank OneNote where I copy and pasted that equation, and that's going to be our starting and ending point. So first and foremost, what we're going to do is we're going to talk about Newton's method. So Newton's method stated that our f x to the n equal to the f x to the n minus 1 plus j n minus 1, so our Jacobian, times our delta x, so the change in x, delta x n. So this comes from Newton's method and actually forms the basis of how we apply this equation to solve for roots. Now, when it works, what we want to find is we want to find that f of x to the n equals 0. That was a terrible 0. Let me try that again. We want that to equal 0 at f to the x to the n minus 1 plus this Jacobian of n times the difference. Actually, let me write out that difference. So let's not use the delta sign here. Let's use x to the n, which, reminder, well, x to the n minus x to the n minus 1. Okay? Let's redo that parentheses. Okay. So we have these two equations that, in a perfect world, this would become this would equal 0, and we'd all be happy, okay? And when that is true, then we're done. We don't have to worry about Broyden's method, and we don't have to worry about Jacobian approximation. But if we want to do this without actually having to do this Jacobian over and over, or if we don't know the Jacobian, then what tends to happen is we kind of have to approximate these two numbers. And when we approximate them, we're going to be wrong to some degree. We're going to have some sort of error. And what tends to happen is that this whole equation does not equal 0. It equals, let's say equals a half. And what you could do, what you could do is you could solve this, get this f of x, and then use this new f of x to calculate a new Jacobian, and then use that new Jacobian to calculate a new f of x, and kind of keep doing that over and over and over until you eventually wind up with a 0. But that's a lot of work, and that's a lot of computing power. So what Broyden suggested was, well, what if we just take these two equations here and subtract them from each other? Because Broyden, he didn't want to have to do these iterations every time he needed to find a 0 of a function, especially a multi-dimensional function. So he wanted an easier approach to it. So if you subtract these two functions, you notice right off the bat that these cancel. And what you're left with is f x to the n equals, that goes to 0, so equal to parentheses j n excuse me, I think I have these backwards. That should be an n. That should be n minus 1. So jn minus 1 times x to the n minus x to the n minus 1. The reason why we can do this is because these two terms here are the same. So you can just distribute. And all this, and another way of writing this is we could actually write it, the change in the approximate Jacobian times the change in x. Okay, that means the same thing. So in the way this function, or this iteration function will work is, as you change j, you change x, it eventually go down to 0. And that works, that's fine. And that does work really well when all the variables you're changing work in the x-axis. But let's say we wanted to move our variable along in the y-axis. Because just a reminder, this is designed for more than one variable at once. So what if we wanted to do instead, we wanted to make it change in the y direction, delta y. Well, this function here, let's further specify that y is perpendicular to x. So y is perpendicular to x. So any change in the x direction, won't affect the y at all, right? So what that's basically telling us is that, the change in y times jn equals the change in y times jn minus 1. Well, that's kind of a problem, because that means this method, as postulated here, can't help us find the variable, or it can't help us find the true 0 if the true 0 lies perpendicular to where the axis we started with. So this is where Broyden came in. Is he thought about, how do we overcome this problem? How do we make it so that this this method will work in the y dimension also? Well, the way he did it is he made a new function to start with, and he called it g. That was a terrible g. Let's try that again. So he made a g. It's called g of delta y. And what he did is as this g, he wanted it to give a relationship between x and y. So the way he did that was he did delta y dot product delta x. So as a reminder, the dot product is it's a way of doing matrix multiplication. And a dot product of two perpendicular axes is 0. And the dot product of two in the same dimension is, well, it becomes those two multiplied directly together, because the dot product kind of gives you, it helps you multiply based off of how perpendicular they are. So he did this delta y times, or dot product delta x over delta x times delta x. So that's simple matrix multiplication on the bottom, not a dot product. And all of that times our function as x of n. So what this does is it gives a relationship between this other variable, in this case y, other variable y, in relationship to our initial one x, and kind of help us move it in other axes other than x. And you'll notice, well, if this thing is truly perpendicular, and this j truly doesn't actually move in this direction, then this dot product will end up equaling 0, and this g will just equal 0. But if, let's say, this delta y is in the exact same axis as delta x, then this will become, x squared up top, x squared on bottom, and that just equals 1, so they should just equal the function as is. And then it can run the gambit depending on how perpendicular or parallel the two axes are. And this whole thing, this whole function here, he used to set to this. So this whole thing became equal to this right here, right? Because this is just a transformation of this. So this then equaled our delta j. Oops. Lost my pen there. Delta j, delta, in this case, since our axes, or our variable that we're looking at is y here, then this x actually becomes a jy. Okay, so we have this guy now. Where do we go from here? Well, what we do is we then use this. We're going to use this to get to this. But the first things first we're going to do is we're going to look at this numerator here. So let's say the function we're giving it has n variables. So this delta y is going to equal a matrix with one column and n rows, right? And delta x is going to be the same way. So it's going to be, one column, n rows. Well, what happens when you do any sort of matrix multiplication or dot products or anything is when you multiply them together, they're going to equal, so let's just do delta xy. When you multiply those two together, you're going to get an n by n matrix, right? And those are big and unwieldy. And since those are so big and unwieldy when you're doing calculations, Broyden had the idea of, well, what if we transpose this x? So if we transpose this x, what we'll get, ooh, that was bad. Let's try that again. So if we transpose this x, which is called delta xt, then we'll get instead of this n by 1 matrix, we'll get a 1 by n matrix. So with one row and n columns. Okay. Now when you multiply a 1 by n n by 1 matrix by 1 by n matrix, that multiplication is a whole lot easier to do because it comes out to being, well, a 1-by-1 matrix. So what Broyden did was he took this here, this guy here, and he flipped these two and then transposed this. So then our updated G delta y is going to equal delta x transposed dot product delta y, all divided by this delta x times delta x. Let's just combine this. Let's make this easy. Delta x squared. All that times f x to the n. Okay? So from here, what we do is let's rewrite this a little bit. And so let's move this f, let's erase it. Let's move this here and move this delta y out there. Since now it's just simple matrix multiplication up here that you can, it's a little bit easier to rearrange and still makes sense. So this then becomes delta x, excuse me, I just said to flip it, and then I proceed not to do it. So let's do f of x n times this transpose of x, all divided by x squared. And all this multiplied by our delta y. If you remember, we set all this equal to this back here, right? So then we have this delta j times delta y. Okay, so switch back to black. These delta y's cancel, and we're left with this function here, which let's separate this delta j. So we're left with jn equals, let's move its second one over, j to the n minus 1 plus this f x to the n over our delta x squared times our transposed x. Okay? So this looks very similar to the final answer, right? And the only difference so far is this numerator. So we had just f of x to the n, and this is the change in f of x minus the Jacobian times the change in x. So we're almost there, and this answer is acceptable. It is there, and I'm just going to show you that this equation here is equal to Broyden's stated equation up top. And the way we're going to do that, let's switch back to green. So we got, so the definition of our, so by definition, the change in f then, that's bad delta. Let's try to draw a better triangle. This change is equal to our f of x to the n minus its previous value, x to the excuse my drawing, minus f of x to the n minus 1. And we're going to rearrange that to say our f of x to the n equals our change in the functions plus our f of x to the n minus 1. Okay, so now we're there. Okay, so we have this equation here. Now what we're going to do is we're going to actually pull these equations all the way up from the front. And you remember one of those equations said we had f of x to the n, equals f of x to the n minus 1 plus our Jacobian times our delta x. And the other one we had was this, which was 0 equals our f of x and that is plus our j n minus 1 delta x, right? Now, if we combine these two in the right way, what we'll get is our f x to the n equals this piece. So we'll get this delta f of n minus our jn minus 1 x to the n. So, excuse me, this should be a n minus 1. So this comes out to delta f at n minus j n minus 1 delta x. And then we substitute this in for that, so this up here. So our final answer then becomes j of n equals j of n plus 1, n minus 1, excuse me. And we have this plus this delta f of n minus our jn minus 1 delta x, all divided by our delta x squared times our x transposed. Okay, so this is our final answer, and this is the same as this up here. So what we did is we there's just a step-by-step derivation of this equation, and yeah, this is just one approach of doing it. There are multiple ways, but this is just the one I'm going to be showing today. So glad you hooked the video, and I'm glad you learned something. Thank you.